So what are conductors? A conductor is a material that allows charge to flow freely through it. Now by charge, I really mean electrons. So most of these conductors are metals. So what's going on with metals that allows charge to flow freely through them? Well, most metals look like this. We've got nuclei down here. Each nucleus has a bunch of electrons that are associated with it. Now, with conductors, with metals, we've got some of these bands where the electrons are held very close to the nucleus. So these blue ones, we know which electron belongs with which nucleus. But then we've got something called a conduction band. Where the electrons can move from one nucleus to the next, to the next, to the next, and it's all okay. So it's this conduction band that allows metals to conduct electricity. All right, how do we characterize this electricity flow? How do we characterize how good of a conductor a certain metal is? Well, we've got an equation that tells us J measures the charge flow, is equal to sigma times E. Sigma is called the conductivity, and it characterizes the metal that we're talking about. And E is the electric field that we apply. We need to apply an electric field because there's no reason for charge to move unless there's an electric field trying to push them. So this sigma tells us the response of charge inside of a metal to an applied electric field. Now, for most good metals, we've got sigma, the conductivity, of the order of 10 to the 8, 100 million in SI units. Now, I'm not going to talk about exactly what those units are yet because we need a little bit more to do that. But just so you know, it's a pretty big number for the good conductors. All right, now an electric field makes charge flow. So if I apply an electric field to a conductor, then the charge is going to flow. Now, as that charge flows, if the electric field doesn't go away, then it'll just keep flowing and flowing and flowing and flowing. So if I've got a slab of good conductor and I apply an electric field to it, then the charges are going to move until there's no more electric field. So that means that if it's a good conductor, then I can take the electric field as 0 inside of it. All right, let's look a little bit at what this means. So the electric field is 0 inside, and what that means is that all the charges inside don't want to go anywhere. They're just sitting there. There's no electric field, so why are they going to go anywhere? So that means that the entire surface of the conductor is at the same potential. Because if there was a potential difference, if it was a higher potential over here than over here, then the electrons would move. But that would mean there's had to be an electric field. There is no electric field. So that means that the surface of a good conductor is an equipotential region. Equa meaning equal, and potential meaning potential. All right, so when I have an equipotential surface, the electric field must be perpendicular to that surface. So if I've got a conductor right here, and I've got an electric field coming in, well, it's got to stop at negative charges because that's where electric fields stop. So it's got to be perpendicular. So I'm going to draw my electric field lines so that they hit the surface of the conductor perpendicular. And that gives us this nice little diagram. No electric field inside. And then because there's negative charge on this side, there must be positive charge on this side, or else the conductor is charged. Now, I don't want the conductor to be charged. I want it to have 0 net charge. So what happens is these positive charges over here generate electric field lines, again, perpendicular to the surface, so that if I were to take the conductor away, then the electric field lines would just go straight across. Like that. Now, you may be wondering, how is it that the electric field is 0 inside? Here's the idea. When we've got this positive and negative, the electric field associated with these positive charges will push this way toward the negative charges. And what that does is it cancels out the electric field from outside. So those two, the contribution from both of those electric fields cancels, and we get 0 inside when we take the whole electric field. And that's generally the way that it works. When you apply an electric field to a conductor, the positive charges will move farther downstream of that electric field. And then they generate their own electric field, which opposes the electric field that I first put on the conductor. All right, now let's look at a slightly different situation. Suppose that I've got a conductor like this with a sharp point. Again, it's a conductor, and that means the electric field lines gotta end perpendicular to the conductor. Now over here, that's fine. Get nice spread out charges. But over at the sharp point, look what happens. I've got these electric field lines that gotta come out in this very strange way. So that means that I've got a congregation of charge over here. So charge congregates at sharp points. You may be familiar with that from Van de Graaff generators where you touch the top and then people's hair goes way up. That's because people behave kind of like conductors, and when you're taking all that charge in, that charge is going to go congregate at sharp points. Well, where are the sharpest points on the human body? In the hair. So that's the way that that works, and that's why you've got hair that stands all out when you touch a Van de Graaff generator. That's conductors.